Hi, welcome to Academic Math. In this video, I will solve the last question of question number 1 of exercise 2 of the book Higher Algebra by Mapa, that is the Abstract Algebra by Mapa books. Exercise 2. In the previous video, we have solved question number 1 and 2 of the question 1. Now, in this video, I will solve question number 3 and 4. Here, a relation rho is defined on Z by A is related to B if and only if a square plus b square is a multiple of 2 is a multiple of 2 for AB belongs to Z. We have to determine the nature of the relation. Question is determine the nature of the relation. Determine the nature of the relation rho. Solution. Let A, B, C belongs to Z. Now, as a square plus a square plus a square a square plus a square equals 2 into a square, which can be written as 2k for k belongs to Z, which is a multiple of 2, and therefore we can say that A is related to A for all A belongs to Z. Also check this also, if A equals 0, then 0 square plus 0 square equals 0, and which can be written as 2 into 0, and which is also a multiple of 2, which implies that 0 is also a multiple of 2. 0 is also a multiple of 2. Now, so therefore we can say that A is related to A for all A belongs to Z, and which implies that rho is reflexive. Rho is reflexive. Determine means the nature, means determine the nature of the relation, means we have to determine that rho is reflexive, symmetric or transitive or antisymmetric on Z here. Now, in the next page, I will show the symmetricity of the relation rho defined on Z. That is, I will check, that is, we have to check that rho is symmetric or not. Let A related to B, we have already taken A, B, C belongs to Z previously. So let A related to B, and which implies that A square plus B square equals 2 into K for some K, for any K, there exists such K, because we have already taken that A is related to B, therefore the square of A, addition of the square of A and B is a multiple of 2, therefore it can be written as 2 into K for any K, there exists such K for K belongs to Z. for k belongs to z. There exists such k because we have already taken that a is related to b. That's why there exists some k belongs to z, which can be written as b square plus a square, and which equals 2k, and we can say that b is related to a, and therefore a related to b implies that b related to a for ab belongs to z এর জন্য, for any ab belongs to z. Now so we can say that therefore we can say that rho is symmetric. We can say that rho is symmetric on z. Now I would like to check rho is transitive or not. Let a related to b and b related to c, which implies that a square plus b square equals 2 into k1, and b square plus c square equals 2 into k2, for k1 k2 belongs to z. There exists k1 k2, there exists such k1 and k2 because we have already taken that a is related to b and b is related to c, and therefore there exists such k1 and k2 belongs to z such that this hold. Now if we add, which implies that a square plus c square plus 2b square equals 2 into k1 plus k2, which implies that a square plus b square equals 2 into k1 plus k2 minus b square, which implies that, sorry, this is a square plus c square, it will be a square plus c square. A square plus c square equals 2 into k1 plus k2 minus b square, which implies that a square plus c square equals 2 into k3, where k3 belongs to z, as k1 plus k2 minus b square, this is also belongs to z. k1 k2 belongs to z we have already taken, and b is also belongs to z, therefore we can say that, which implies that a is related to c. Hence we have a related to b and b related to c implies that a related to c, therefore rho is transitive on z. So we have checked the reflexivity, transitivity and symmetricity of the relation rho. Here rho is transitive, we have seen that rho is transitive, and here we have seen that rho is symmetric, and here we have seen that rho is reflexive, symmetric and transitive. Hence rho is an equivalence relation, hence rho is an equivalence relation. Now we will check the antisymmetry of the relation rho. Let a related to b and b related to a, which implies that a square plus b square equals 2 into k, for k belongs to z, and that is b square plus a square is also equals to k. But from these two identity we can't say that, which does not imply, we can't say that a equals b. From these two identity we can't say that a equals to b. For example, if we take a equals 4 and b equals 2, then a square plus b square equals 4 square plus 2 square, and which equals 16 plus 4 which equals 20, which is a multiple of 2, and this is also equals b square plus a square. But it can be written as 2 into 10, where 10 belongs to z. But we can't say that but a not equals to b, that is 2 not equals to 4, and therefore we can say that rho is not, which implies that rho defined on z is not an antisymmetry. Rho is not an antisymmetry. Is not an antisymmetry. Therefore we have check the nature and determine the nature of the relation rho on z here. Now I will check the nature of the relation rho of the next question, that is question number 4 of book 1, that is question number 1.4. In this question it is given that AB belongs to Z and the relation rho is defined on Z. The relation rho is defined on Z by A is related to B if and only if 2A plus 3B is divisible by 2A plus 3B is divisible by 5. That is, we can say that 2A plus 3B equals 5 into K for some K belongs to Z. We have to determine this question is also, in this question we have also determine, we have to determine the nature, determine the nature of, determine the nature to determine the nature of the relation rho on Z. This is the question. Now we will solve this question, that is, let AB belongs to, also C, also take C belongs to Z. Now 2A plus 3A equals 5 into A, and which is a multiple of 5, that is, as 5 divides 5A, which implies that A is related to A for all A belongs to Z, and which implies that rho is reflexive. This is the first relation, that is with the reflexivity, to check the reflexivity. And next step, in the next step we will show that rho is symmetry. Now let A is related to B, which implies that 2A plus 3B equals 5 into K1. Suppose 5 into K1, because we have already taken that A is related to B, and therefore there exists such K1, there exists such K1 belongs to Z. Now we have to show that 2b plus 3a, to show that 2b is related to a, 2b plus 3a. If we can show that 2b plus 3a is a multiple of 5, that is 5 divides 2b plus 3a, then we can say that b is related to a. And 2b plus 3a can be written as 5 minus 3 into b plus 3 can be written as 5 minus 2 into a, and which equals 5b minus 3b plus 5a minus 2a, which equals 5 into b plus a minus 3b plus 2a, that is 2b plus 3a equals 5a plus b minus 3b plus 2a, which equals 5 into a plus b minus 5 into k1, using the relation using equation 1. 3b plus 2a can be written as this, because 3b plus 2a is equal to this, equals 2a plus 3b. 3b plus 2a and 2a plus 3b are the same. This is equals to 2a plus 3b also, because addition is commutative on z, and therefore 5 into a plus b minus 5 into k1, and which implies, sorry, this equals, which equals 5 into a plus b minus k1. As a plus b minus k1 belongs to z, hence we can say that, therefore we can say that b is related to a, as 5 divides 2b plus 3a also. And therefore a is related to b implies that b is related to a, hence row is symmetric. That is, we have take the two important things, row is reflexive and row is symmetric. Here row is reflexive and here row is symmetric. Now I will try to show that, I will try to check that is row transitive or not. To check the transitivity of row, let a related to b and b related to c, then 2a plus 3b, there exist k1 and k2, 5 into k1 and k2, such that 2b plus 3a equals 5 into k2. There exists such k1, k2 belongs to z. Okay, now adding these two equations, last two equations, we have adding these last two equations, we have 2a plus 3b plus 2b plus 3c equals 5 into k1 plus k2. Since k1 k2 belongs to z, therefore we can say that k1 plus k2 is also belongs to z, which implies that 2a plus 3c equals 5 into k1 plus k2 minus 5 into b. Adding these two, 2a plus 3b, 2b plus 3a, these two are symmetric term, and therefore we can add them, and 5b, and we can common we can take common 5 from the right hand side, and which implies that 2a plus 3c equals 5 into k1 plus k2 minus b, and which implies that 2a plus 3c equals 5 into k3, where k3 equals k1 plus k2 minus b, and which is also belongs to z. And we can say that a is related to c, therefore a is related to b and b is related to c, for abc belongs to z, implies that a is related to c, and therefore rho is transitive on z. So we get another observation that rho is also transitive on z. So therefore rho is reflexive, symmetric as well as transitive. This is an important relation. 2a plus 3b, this relation is an important relation. 2a plus 3b equals 5k1, this is an important relation. We can say that this is an equivalence, in fact this is an equivalence relation, and therefore rho is an equivalence relation on z. Now I will check the last nature, that is check the antisymmetry of the relation rho. To check, let a related to b and b related to a, which implies that 2a plus 3b equals 5 into k1 and 2b plus 3c equals 5 into k2. Is the last two identity. From these two last identity we can we conclude that rho is antisymmetry or not? Can we conclude that? Can we conclude that rho is antisymmetry or not? Can we conclude that a equals b? If we conclude that a equals b, then we can say that rho is an antisymmetry. If we can't conclude that a equals b, then we can say that rho is not an antisymmetry. Now I will try to show that rho is not an antisymmetry, but that is there exists some a b not equal to a, and which hold the two identity, this and this. Here it is given that 2a plus 3b equals 5 into k1 and 2b plus 3a equals 5 into k2. For example, if we take a equals 1 and b equals 3, then then it will satisfy the first equation, and it will not satisfy the second equation. If we take a equals 4 and b equals -1, then we can show that if we take a equals 4 and b equals -1, then 2 into 4 minus 3 plus 3 into -1 equals 8 minus 3, and which equals 5, and which is a multiple of 5. 5 into 1 we can write it, and 2b plus 3a equals 2 into -1 plus 3 into 4, which equals -2 plus 12, and which equals 10, and which is also a multiple of 5, but a not equals b. Hence we can conclude that conclude that a related to b and b related to a does not imply a equals b, and therefore the relation rho defined on Z is not an antisymmetric. Hence completes the first question of the book Higher Algebra by Mapa, that is abstract algebra of exercise 2. And in the next video I will try to solve the next question, that is question number 2 and question number 3. Thank you. All are requested to comment if there is any problem related to the video. Thank you.